Okay, guys. Oh, God, I look bad, don't I? It's the lighting, I swear. All right, this is going to be just going to go over some of the questions that are in the book. Mostly math questions, some conceptual questions, but the conceptual questions usually have a pretty good explanation right next to them, so you should be able to get those. But the math, we're just going to run through that just to kind of make sure you guys have got it. That's it. I'm going to pause this. I'm going to use my computer as a tablet, so I'm going to probably get rid of my beautiful face here too. Okay, so I'm doing this off the clock, which means, I think that means that I can sip a Manhattan while doing this, which is really the only way to work. Okay, so chapter 3, we have, there's not a whole lot. Let's just look at number 24. So chapter 3, 24, this is page, there's really no need for the G, is there? 45, number 24. And let's see, what is the wavelength of 3 megahertz sound in soft tissue? Okay, wavelength. What is the equation for wavelength, guys? Wavelength, let's see. Wavelength is equal to what? C over F, right? Let's put units back in there, wavelength and millimeters, speed of sound in millimeters per microsecond. So what the hell did I just do here? Hold on. Yeah, let's get rid of that. Millimeters per microsecond. It's a microsecond and megahertz. Okay. Let's plug in numbers for number 24. Do we know? You know, we're looking for lambda, so we'll leave that. But what's C? What is C, guys, in millimeters per microsecond? Right, 1.54 microsecond. And frequency is given as 3 megahertz. Okay. Now, here's, and so far so good. Actually, if we divide these two, we are going to get, you know, as you might guess from looking at the question, 0.51. In fact, let's go ahead and just put that in, 0.51. But what they're kind of asking here is, what are the units? Because they're kind of giving you the math, right? And if you, of course, if you take out your calculator and do 1.54 divided by 3, you will get 0.51. What's the deal with microseconds? Nice screen. Microseconds and megahertz. One is a millionth of a second. The other is a it was a million seconds. Yeah. Just wondering how I said that, but they cancel. Even though it's microseconds and megahertz, it sounds like, why would those units cancel out? Usually it's millimeters to millimeters cancel, or seconds to seconds cancel. They do. Millionths and millions cancel. And so we're left with millimeters. So 0.51 millimeters. That would be letter C is the correct answer for that one. Let's look at 25. What is the wavelength of the wave? Oh, and the other thing I want to talk about, let's talk about with the second one, 25. What is the wavelength of a wave with an unknown frequency traveling in soft tissue? Okay, there's no math on this one. Unknown frequency. This is, once again, this is just a units And we could pretty much know right away that if you're looking at the book, it's letter E, because once again, millimeters. Here's the question for you. It says basically, what is the wavelength of a wave with an unknown frequency? Traveling in soft tissue. Question, guys. Is this extraneous information? You know, a lot of times questions give you extra information you don't need just to throw you off. Is that extraneous information? Oh God, that's good. All right. No, it is not extraneous information. C, as we know it, as 1.54 millimeters per microsecond, is the speed of sound in soft tissue. So soft tissue is an important part of this question. Without it, we don't know what C is. And remember, you change C, you change 1.54, you keep your frequency, something's got to give, right? And so the wavelength will change. All right, let's move on. So that was 24, kind of 25. 26 is the same question all over again, except this time they're actually asking what the number is. So let's go ahead and let's just do it real quick. I'm not gonna, you could read along. What is the wavelength of, so wavelength, millimeters, of 2 megahertz sound in soft tissue. So soft tissue, 1.54 millimeters per microsecond. And we said 2 megahertz. Microseconds and megahertz cancel. So it's 1.54 divided by 2. I could pull out a calculator and do that, or I could, honestly, I could just look at the answer right here, which is what I'm going to do. I think it's 0.77, right? Yes, so letter B is 0.77 millimeters. Always do your units. If there are units involved, do the units. What are the units for duty factor? Trick question, no units. Okay. Let's see, I think I wanted to, okay, let's move along here. So not a whole lot of questions in chapter, what was that chapter? That was chapter 3. Chapter 3 that I wanted to work on with you. Okay, I think page 59. And let's see. Let's do one. Okay. Which of these 4 values, and I'll write the 4 values down, for pulse repetition frequency would have the longest pulse repetition period? Okay. So let's do this. Pulse repetition frequency, and they're going to give us 4 values, A, B, C, and D. First is 2 kilohertz. Second is 4,000 hertz. C is 6 hertz. And D is 1 kilohertz. P, pulse repetition frequency, the number of times the machine is pulsing per second. Okay. Let's write this so that they're all the same, or they're all the same units, because we have kilohertz and hertz in here. 2 kilohertz, that's the same as saying 4,000 hertz. We already have this one. Let's just write it again. 4,000 hertz. 6 hertz. And the last one is 1,000 hertz. And what we're looking for the longest pulse repetition period. So it's a PRP, which is the longest. It's my little PRP muffin. Okay. All right, guys, right off the bat. Let's say you're confused. You can't, for the life of you, you cannot remember. Oh my God, is it directly related? Is it indirectly related? I can't remember. Look, there are two outliers. You're asking for the longest. You can't remember which one's which. Fine, at least give yourself a 50% chance, right? 4,000 hertz is the biggest number over here, and 6 hertz is the smallest. It's got to be one of those two. Scratch out those others. This isn't knowledge, this is strategy so far. The strategy is now you have a 50% chance of guessing correctly. Now let's use knowledge. Pulse repetition frequency and pulse repetition period. They are in fact reciprocal. They're inversely related perfectly, which means they're reciprocals. Okay, so 1 over PRF is equal to PRP, 1 over PRP is equal to PRF. That means reciprocals, if one goes up, the other goes down. If one goes down, the other goes up. Okay, so we're looking for the longest PRP. So longest over here, so we're looking for the, in other words, the biggest number, right? Longest, biggest number. So we're looking for the smallest number over here. The smallest number, 6 hertz. Let's draw this out exactly what that means. Just as a reminder, let's remember what this means. Oh, guys, this is awesome. I'm gonna do these more often if I can, if I have the time, and make these your asynchronous assignments. Now that's a good use of time. I love it. Okay, PRF. So here is our current pulse repetition frequency. I don't know what it is. It's just the current one. The pulse repetition period is all of that. Now, let's add another pulse in there. I've increased my frequency. I've gone from 2 to 3 or whatever, 2,000 to 3,000, whatever that means, but 2 to 3. Now look at my pulse repetition period. So I've increased my pulse repetition frequency and I've decreased my pulse repetition period. Obviously, this is less time here than here. Okay. Oh, number 2. I looked at that one earlier. Come on, baby. Number 2 on page 59. 4 pulses have pulse repetition periods as listed below. Which of the following 4 waves? Okay, this is, a lot of times the questions are worded differently. It's done on purpose to make you think. So in other words, it's not just rote memorization. However, this is really poorly worded. 4 pulses have a pulse repetition periods. All right. How about 4 beams have a pulse repetition? 4 ultrasound machines. 4. It's not pulses. The pulses are components of the pulse repetition period. So that's a poorly worded. And then which of the following 4 waves has the highest pulse repetition frequency? An 8-second wave. What does that even mean? So 4 waves. Yeah, I honestly don't even know how to interpret that. It's so poorly worded. Once again, let's do this for pulse repetition periods. So PRP is, let's bring everything to seconds. 8 second, that was weird. 8 seconds. That's A, B, C, and D. 8 seconds. 80 milliseconds. So a millisecond is a thousandth of a second, but there's 80 of them. Dear God, what? Oh, my eraser is gigantic. I think I wrote that correctly. 5 milliseconds. So I think that 0.123, because so you count zeros, right? A milli is a thousandths. 1,000, you count zeros. So, well, you count these zeros, and then there's 3 zeros, so it's 1, 2, 3. This would have been 3 as well, but there was 80 of them, so it's 1, 2, 3, but 8. In D, 400 kiloseconds. Who the hell counts 400 kiloseconds? It doesn't even make sense. So that's actually 400,000 seconds. Okay, I forgot what we're even looking for here. But whoops. But let me just look at something. The outliers. Strategy. Once again, what are the outliers? Let's see. 4,000 is the largest, and 005 is the smallest. So these are the outliers. Give me a pretty green. All right. These are the outliers. So gone. You don't even really have to understand what you're talking about. You just, if it's looking for, well, what is it looking for? Number 2. Which of the following 4 waves has the highest pulse repetition frequency? So pulse repetition frequency. This is the same. I just noticed that. This is the same thing as what the question like we just answered this question. So once again, if this goes up, that goes down. But we're looking for the greatest pulse repetition period, right? Which has the highest pulse repetition frequency. So highest, so arrow down, we must be looking for the smallest number. Better be C. Yes, it's C. And we could find out what this is. I need my phone here for a calculator. 1 divided by 0.005. Let's write that. Let me show you what I'm doing. So the PRF is 1 over PRP. It's the same thing. So 1 over 0.005, 0, and that equals 200. 200. Yeah, we changed everything to seconds. So that should be the pulse repetition. Wait a minute. If we're looking at 5 milliseconds. The pulse with the shortest pulse duration will have the highest pulse repetition frequency. 5 milliseconds. So oh gosh, I have to think about what my units are, right? I've changed everything to seconds over on this side. Pulse repetition frequency, 200 hertz. Duh, 200 per second, because I've already changed things to seconds. Second. Yeah, oh, even I'm learning something new, right? Okay, do I need number 3? The shortest pulse repetition period. Well, 3 is the same difference. Let's just, I'll abbreviate number 3 here. I'm follow along. Which of these 4 pulse repetition frequencies, PRFs, see before, we were starting with the periods before, right? Well, okay. It's still arrow up, arrow down, right? Because they're asking for the shortest pulse repetition period. So if we're looking for the shortest pulse repetition period, we're looking for the smallest, then we must be looking for the biggest number over here. The smallest number over here is got to be equal to the biggest number over here. So let's see. I'm just going to put 12 kilohertz, so that's 12,000 hertz, 6,000 hertz, 20 kilohertz is 20,000 hertz, and 1,000 hertz. 1 kilohertz is 1,000 hertz. Let's right off the bat. What's let's see, the absolute largest is this one, and the absolute smallest is this one. So if you don't know what you're doing, get rid of those two. 50% chance of getting us right. But we already know we're looking for the highest PRF to get the lowest PRP. Must be this one. It better be. What was this, number 3? ABC. Yes, good. C. And 1 over 20,000 is going to be a 0.00005. Now that I've asked the question, I got to find out, right? 1 divided by 20,000. 0.000, 4 zeros and a 5. 0.00005. 1, 2, 3, 4, 5. Oh, okay, cool. Almost a million. Almost a millionth. But not quite, huh? Actually, halfway there. Okay. Let's move it on up to the sky. You guys are probably not familiar with that show. Okay. Hey, and if you guys ask me specific questions, text me. Say, next time, can you do page 60 whatever and show me something? Let's see, 62, and let's see, 62 number 1. 62, page 62, number 1. I think I looked at this. I don't want to. Yeah. So, duty factor. I said duty. Duty factor. What is that? Duty factor. What's the units here? No units, but we can say it's a percentage if we want, right? So duty factor percentage is equal to, what is that? It's a duty factor. It is the time talking, the percentage of time talking. So we're going to put talking time, pulse duration, divided by the pulse repetition period. Let's draw something else really quick. One. This is one PR. I have a habit of doing that. PRP, and this is one PD. Time it takes for one pulse. By the way, what if I asked you to find the duty factor and I gave you the pulse repetition period, but I didn't give you the pulse duration? Instead, I gave you the number of cycles and the period. Could you still find duty factor? Yes, you can. Okay. Number one, if all other factors remain unchanged, what happens to the duty factor? Increase, decrease, remain the same when the pulse repetition frequency increases. Let's draw this out again. This time, let me draw this out a little bit bigger. So if you have trouble remembering things, then learn how to draw better than that. Okay, a bit of an uphill, but that's okay. Let's put a pulse here, and we'll just put a pulse at the other end. Okay. So, which is going to have a greater duty factor? This picture or that one? By adding another pulse in here, what I've represented graphically is a higher pulse repetition frequency, right? Without the pulse, it's whatever, pulse repetition frequency 2,000, whatever the number is, let's call it 2. Now the pulse repetition frequency is 3. The percentage of time, whoops, let's just do that a little prettier. Pulse duration, pulse repetition period. Is this percentage of time talking? Is that greater than that percentage of time? So we get rid of that down there. In other words, when you've increased the number of pulses in a time period, well, in a second, more time talking, less time listening. So duty factor is your percentage of time talking must go up. Mathematically, of course, you could figure that out as well. Let's just do it with arrows like I like to do. We haven't used purple in a while. If the pulse repetition period goes up, the duty factor will go down. Damn it. All right. If the PRP is greater, and it is greater on this, on my original 2 pulse line, pulse repetition period was greater, less. Okay. All right. That's number 1. Number 2, I think I'll just talk it through. If all other factors remain unchanged, what happens to the duty factor when imaging depth? Depth. Actually, I do want to draw this one. The depth increases. Okay. I will draw this as, I'm going to draw it horizontally, even though I usually like to draw depth like this, because that's how we scan, but I'm going to go ahead and draw it horizontally versus deeper. Okay. This maximum depth is there. I'll just go ahead and put a pulse and a pulse, but let's put echoes coming back, and I'll put the echo here. So if all the factors are going to change, when imaging depth increases, what happens to the duty factor? Okay, right. Because we remember, you guys know we have to wait for all the echoes to return. Okay, so on a shallow depth, this is our shallow. Once again, I got the ugly green. Okay, echoes are coming back. And it takes whatever, 26 microseconds for them all to come back, whatever the number is. And then the next one goes out. Or we can go deeper and have echoes come back, and come back, come back, come back, come back. What does all of this represent? Listening time. You've increased your listening time when you've increased your depth. Factor is equal to pulse duration over pulse repetition period. So listening time has a big effect on the PRP. All right, if we call this whole area, that's a PRP here. We call this down here the PRP. Well, that's the same as saying the PRP went up, the duty factor went down. Okay. 7:23. All right, I've got to pause this and go pick up my wife. Yike. Oh, I'm not plugged in either. That's not good. All right, pause recording. I'll be back. No time will pass for you. It'll be magic. And like magic, I am back, and we have some new stuff on the screen. Fortunately, I only took a few sips of that Manhattan before I had to go pick up my wife. But now I could chug the rest. Okay. I jumped to page 65 and look at questions 3 through 6. It uses these little illustrations here, and I kind of drew them really poorly, actually, but deal with it, guys. No, it's okay. The first one, shows a wave form like this. Okay. So again, I got an ugly wave. The second one, let's see, there's a wave in the beginning and a wave at the end. The middle one, or the C, I should say, is no wave at all. And then this one has a wave here and here. And it shows something there, but that's irrelevant. Okay. So question 3, what are the duty factors of the 4 patterns that appear? Okay. This one can be a little tricky. Hopefully A is not tricky. The duty factor is basically 100% of the time that is talking. It is talking 100% of the time. It's also listening 100% of the time, but it's talking 100% of the time. B, 33% of the time. Now, wait a minute. I'm sorry, I said the answer before we talked about it, but well, let's go ahead and write it down since I spilled the beans. But, you know, when you first look at this, you might think, well, wait a minute, there are 4 spaces here, right? There's a space here, there's a space there, space there, space there. So 4 spaces, and 2 of them are filled with talking, and 2 of them are not. So wouldn't that be 50% of the time? And the answer is no for that, because what is a pulse repetition period? It is, well, let's choose to look at here. That's a pulse repetition period. 1 pulse, and the time it listens is a pulse repetition period. So that means 3 sections that, you know, whatever sections these are, this is just an example, right? So it's 1/3. 1/3 happens to be 33%. That is why B is that. Talking time apparently is 0% here. And down here, now this one's 50%. Sorry, I keep looking at the answer before we talk about it. But once again, it is the time period of 1 pulse, 1 listening period, and these are evenly spaced, so there's as much of a pulse as there is a listening period. This is an unrealistic number. Even 33% is unrealistic. 0%, the machine's off, and 100% is a continuous wave transducer. Number 4, which of the patterns in figure 4.13 indicates a system with a superficial imaging depth? Okay. The superficial imaging depth. Remember, we talked earlier about scanning maybe that deep versus scanning that deep. And on each one of these, we only have 1 pulse, because you only send out 1 pulse at a time, right? And then I drew echoes. Ugly green again. All right. And then for here is echo and echo and echo and echo. And in other words, the time it takes for all of this listening period is a lot more for the deep. So duty factor goes down, but let's see. For indicates a system with a superficial imaging depth. So this is superficial. I mean, we know that because it's a shorter depth entirely. But look what else is going to happen with this one. The next pulse is going to go out sooner than if you were imaging to this depth. So it's sooner, it's faster, it's a higher duty factor. It is this one, the 50%. Once again, an unrealistic number, but these are just illustrations. My stupid dog scratching. So let me hit, and the dogs are in, the cats are in. Cats are fed, dogs have not been fed. I have not been fed. So I just have to feed myself. Anyway, anyhow, no, that's just how we swing here in the Schellenbach residence. The next couple of questions are actually pretty easy. Number 5 is the opposite. Number 4, that's the shallowest imaging depth. Well, C is not imaging at all. It's off. So I guess it's got to be B, right? Yes, B. Choice B is the deepest imaging, and even 33% is unrealistic. That would be extremely, extremely shallow in real life, but that's okay. We're just, like I said. And then number 6, which two of the patterns identify an altar system that cannot perform anatomic imaging? Well, if you're not talking at all, letter C. And if you're continuous wave, no imaging allowed with continuous wave. So A and C are the answers there. Ooh, right. So as we go to page 66, we have another illustration. The following 9 questions. You're gonna have to follow along because I'm not redrawing this, at least not right now. Which of the following describes line A? Can we say frequency? No. Well, how about period? No, it's not period either. Duty factor? Well, no, it's not duty factor. It is the talk time, but it's not a percentage of talk time, right? So it's not the duty factor. B, pulse repetition period. No, it's only one pulse. Pulse duration. Yes, pulse duration. That's the one thing it works, amplitude. I'm going to hold off on the rest of these for now because they should be easy enough to follow. Just looking at number 18 really quick. This might be the last one I do right now. I'm running out of time, and that's okay because I'm going to do more of these. I'm going to catch up to where we are in the book and continue to work with you guys on this. 18 on page 67, the speed of a 5 megahertz continuous wave. Okay. Why? So I'm a little suspicious already. I haven't even read this one yet. I'm just going to draw. It says continuous wave. I'm going to draw it out. I haven't even read the whole question, and I have a feeling that drawing it might be helpful. Maybe not. I'll never learn, will I? Okay. So this is number 18, page 67. The speed of a 5 megahertz. Okay, we know it's 5 megahertz. Now, in this case, remember, when we're talking about pulses being 5 megahertz, well, yeah, it's 5 megahertz, but it's only one tiny little piece of that 5 megahertz. But this is continuous wave. So the whole thing is 5 megahertz. Okay, the speed of a 5 megahertz continuous wave is 1.8 kilometers per second. Seriously? Kilometers per second. I'm already suspicious. And that's, you know, really, that's why they're giving us that. The wave is then pulsed with a duty factor of 5. Oh, come on. Now we've pulsed it. Doesn't make any sense. So, and that's okay. These questions don't have to make sense. They're questioning whether or not you know what you're talking about. So now it's pulsed at what was it? Duty factor of 5. Well, let's kind of draw it like, let's draw it like the other one. Except we'll have, I'm sorry, 0.5, which is, ooh, no, 0.5 is not the same as 50%, is it? No. Hitting the wrong button. Okay, so pulse, and we'll say, okay, duty factor is equal to 0.5. Calculate the new propagation speed. Okay, so I wish I just read through the whole thing, right? Right, because here I am. I'm drawing all these. I'm drawing this pretty picture of a continuous wave, and then a pulsed wave with a duty factor of 5, and it's the 5 megahertz frequency operating is equal to 5 megahertz, and it's 18 kilometers per second. And let's just read what the answer is. The propagation speed for pulsed and continuous wave sound is the same. In this case, 1.8 kilometers per second. So that's a great example of useless or misleading info. Useless or misleading info. The 5 megahertz is useless. The duty factor is useless. The fact that it's continuous wave versus pulsed is all useless information. Speed of sound is the speed of sound. It does not change in a tissue. Changes between tissues, but not in a tissue. All right, I'm gonna call it quits right here. Like I said, guys, let me know if you have certain questions in this book that just confused you. Let me know. If you are not going through this book on your own time, like I said, I've kind of left this up for you. If you're not doing this on your own time, you're done. You're not going to make it. So I'm just going to say it right there, because I've had enough experience with enough of students to know you're not going to make it. So do these on your own time. All these questions, understand them. Like I said, if you don't, let me know. I'll make a video for it. All right, signing out. Adios.